Video 13 ended on a gap. Every deep network so far learned by finding structure in something physical. Pixels arranged on a grid, sound arranged in a waveform. A network could discover edges because edges are really there, sitting in the data, waiting to be found. Words don't work that way. There's no edge hiding in the letters CAT, no pixel grid underneath love or Tuesday or almost. And yet, by the early 2010s, networks were reading, translating, and predicting language with real success. So here's the actual question this video answers. If a network can only learn from structure and language has none of the physical kind, what did researchers give it instead?
Plain machine. AI in plain English. We're tracing the complete history, from the very first idea all the way to the present. Let's continue.
Think about a well-organized record store, back when those existed. You wouldn't find Bach shelved next to Metallica, not because of alphabetical order, because of relationship. Genres cluster. Related artists sit near each other, not because someone wrote a rule about it, because customers kept looking for one after buying the other. Proximity in that store means something. You could walk in never having heard a record, glance at what's shelved beside it, and already know roughly what you're about to hear. That's the trick researchers borrowed for words. Instead of shelving records, imagine placing every word in a language somewhere in space, not on a shelf, but as a point with coordinates, hundreds of them. Words that show up in similar situations, king and queen, dog and puppy, Paris and London, end up near each other. Not because anyone told the system they were related, because the system watched how those words behaved across millions of sentences, and words that behave alike end up sitting close together. Distance in that space isn't a metaphor, it's a number the network can actually compute. That point in space, one word, one location, hundreds of coordinates, is called an embedding. Here's what makes it strange the first time you see it. Once every word has coordinates, you can do arithmetic on meaning itself. Take the location of king, subtract the location of man, add the location of woman, and land somewhere in that space, and the nearest word to where you land is queen. Nobody programmed that relationship. It fell out of the geometry because king relates to man the same way queen relates to woman, and that pattern showed up consistently enough across enough sentences that the coordinates encoded it on their own. The method that made this possible has a name: Word2Vec. Published in 2013 by a research team at Google led by Tomas Mikolov. The idea is almost embarrassingly simple. Take a massive amount of ordinary text, news articles, books, whatever's available, and slide a small window across it, word by word. At each position, the network's job is to look at the words surrounding a target word and guess what that target word is. Or run the other direction. Look at one word, guess what's likely to surround it. That's the entire training signal. No dictionary, no grammar rules, no human labeling a single example as correct. Just, given this context, predict this word. Millions and millions of times, across a text corpus large enough to make the guessing genuinely informative. Every time the network guesses wrong, it adjusts. The same back propagation mechanism from video 10, nothing new there. What's new is the target. Instead of learning to classify an image, the network is learning to compress each word into a location that makes its neighbors predictable. Words that predict similar neighbors end up in similar places. That's the entire mechanism. Context did the labeling. Nobody else had to. Let's make this concrete with the example that convinced people this wasn't just a clever trick. Every word Word2Vec trained on has a location, hundreds of coordinates, one per learned dimension. Take the coordinates for king, subtract the coordinates for man. You're left with something like royalty minus male, not in words, just in numbers. Now add the coordinates for woman. Land on a new point in that space. Search for the nearest actual word to that point. It's queen. Try it again with countries and capitals. Paris minus France plus Italy lands you near Rome. The relationship, capital of, turned out to be a consistent direction in the space, one you could apply to a different country and get a sensible answer. Nobody built a rule that says capital cities work this way. The network never saw a definition of capital. It only ever saw millions of sentences where those words showed up in predictable company. And predictable company, it turns out, is enough to encode a relationship as pure geometry. Word2Vec didn't stay a language experiment. Once researchers proved that meaning could be compressed into coordinates, the same trick spread everywhere something could be described by its context. Recommendation systems started embedding products. Two items purchased by similar customers end up close together, the same way dog and puppy do. Search engines started embedding queries, so a search for affordable laptop could surface pages that never used those exact words because their embeddings sat nearby. Even non-text data got the treatment. Genes, songs, user behavior, anything with enough surrounding context to define it. The core insight generalized past language entirely. You don't need to hand-define what something means. You need enough examples of what it appears near and a network willing to do the arithmetic. By the mid-2010s, embeddings weren't a language technique anymore. They were a way of thinking about data itself. Here's where the honesty matters. Word2Vec gives every word exactly one location in that space, permanently. Bank gets one set of coordinates, just one. But bank means something different in riverbank than it does in bank account. And a static embedding can't tell those apart. It has to average the two meanings into a single point, or lean toward whichever sense showed up most often in training, and hope context elsewhere in the sentence does the rest of the work. For a lot of practical tasks, that was good enough. Search, recommendations, basic translation all improved measurably. But for anything that required actually understanding a sentence as it unfolds, the limitation was real, and it was structural, not a bug you could patch by training longer or on more text. The word's coordinates don't move depending on what's around it. They're fixed the moment training ends. Think about how differently you'd read the word crane in "the crane lifted the beam" versus "the crane flew south for the winter." A human resolves that instantly using the rest of the sentence. A Word2Vec embedding has already committed to one meaning before it even sees the sentence. That gap, one fixed vector standing in for a word that actually changes meaning depending on its neighbors, is the problem the field spent the next few years solving. Not by throwing out embeddings. Embeddings were right. What was missing was a way for a word's representation to shift in real time based on the specific sentence it appeared in. That single fact becomes the entire premise of the next video in this series. Let's put the full shape of this together. Deep learning taught networks to find structure inside pixels and waveforms, physical signals with edges and shapes already sitting in the data. Language offered no such structure. So in 2013, a team at Google, led by Tomas Mikolov, gave the network something else to look for: Not physical structure, but statistical company. Which words tend to show up near which other words across millions of sentences. Word2Vec turned that company into coordinates. Coordinates turned into geometry. And geometry, it turned out, was enough to encode relationships nobody explicitly taught it. King to queen, Paris to Rome, dog to puppy, all as consistent directions in space. Here's the tweetable version. Word2Vec didn't teach a network what words mean. It taught a network where words live, turning king, queen, man, and woman into points in space where the distance between them encodes meaning itself. That's not a dictionary, that's geometry standing in for understanding. Act 4 has a starting point. Words became vectors. What comes next is teaching those vectors to move. One fixed vector per word got the field remarkably far, but it left a specific gap open. A word's meaning needs to shift depending on its neighbors, in the moment, not settle permanently during training. That's the exact question video 15 picks up. What if a network could look at every other word in a sentence, decide which ones actually matter for understanding this one, and adjust its representation on the fly? That mechanism has a name too: attention. It's the idea that made the modern era of AI possible, and it starts in the next video. Subscribe if you want to see how a word finally learned to change its meaning depending on the sentence around it. The AI glossary is in the description. 30 terms, plain English, free. This is Plain Machine. Thanks for watching.